kids, and welcome to Crazy Grandfad Science with me, Crazy Grandfad. Last time we looked at the effect of temperature on water. Now that is part of a branch of science called physics, how things react in the real world. And another important thing as well as temperature is the pressure on something. So what is pressure?
I know what pressure is. Have some pressure.
Yes, thank you, Monster Fad. I think they know that sort of pressure, where you press on your thumbs with something or your fingers. What I'm talking here is about air pressure. That's the pressure of all of the air surrounding you in the room in which you're sitting right now. You don't feel it because you're really used to it, but it is there pressing in on your body all the time. That's called atmospheric pressure. Don't believe me? Let me show you. So I've got a pair of weighing scales here and a cup. What I'm going to do is fill the cup up right to the very top with water. And then we have a look here at how much that weighs, and that weighs 474 grams. What I'm now going to do is put this piece of card, I've got a piece of birthday card here, I'm going to put it on the top of the glass. Then what I'm going to do now is I'm going to turn the glass of water upside down, and then I'm going to let go of the card. And what do you think is going to happen? It's 474 grams of water in there. That's quite heavy, isn't it? What happens if I let go of the card? You watch. Oh. The card is staying fixed on to the glass. Can you see that? I can put it over my head. Crazy Grandfad! And what's happening here is that although there's a weight of water in the cup, there's air pressure pushing up on the card. You can't see the air, but it's pushing up in all directions, including up onto that piece of card. And what that's doing is it is supporting all of that weight of water inside the cup. So although you can't see air pressure, this shows that it does exist, look. There's no trick here, look. I can turn this back upside down and I can take the card off there. And look, I'm getting wet now. So that shows you that air pressure does exist, doesn't it? The reason that there is this atmospheric pressure is because of the weight of air above you. What, Grandfad? You're crazy. Air doesn't weigh anything. Well, yes, it does. If air didn't weigh anything, then it wouldn't do this. Or this. Or this. It has a mass, it has weight, and if it moves around, it can do an awful lot of damage in a storm. You remember last time we said that one of those white fluffy cumulus clouds in the sky has water in it that weighs as much as 2 fully grown blue whales. So what's keeping all of that water, those blue whales if you like, up in the sky? And the answer is the mass of the air in the rest of the sky. You can't see it, but it is there and it weighs an awful lot. Do you have a thick duvet at home? Perhaps it's on your bed, perhaps it's on your mummy or daddy's bed, perhaps it's on your granny's bed. And if you climb under it and you get all snuggly and warm, don't you feel the weight of that duvet pressing down on your body in the bed? That's a little bit like the air in the atmosphere. Each little bit of air doesn't actually weigh all that much, but there's an awful lot of it in the sky. If you measured from the ground up to the top of the sky, where it starts to turn into space, that's about 12 kilometres worth of air, or 7.5 miles. That's an awful lot of air pressing down on you. And that's what atmospheric pressure is. It's all around you, pressing in on your body. So now you understand what air pressure is, let's talk a little bit about the effect that that air pressure has on water. It actually changes the temperature at which water will change from ice into liquid water, and particularly when liquid water turns into steam or water vapour. Now, to explain what's going on here, I'm going to talk to you about something called a phase diagram. Now, this is a little bit more complicated, so if you don't understand what's going on, don't worry about it. And if you want to skip forwards in the video to get to the experiment associated with this, then skip forwards to this time here. Are you still with me? You must be the brainy ones, the buffins. Seriously, if you don't understand this next bit, don't worry about it, it's not a problem. That goes for the adults watching as well. This is called a phase diagram, and this is the phase diagram of water. This tells you for a particular temperature or a particular pressure whether the water is going to be a solid, a liquid or a gas. So on this line up here, if you go up here, you're increasing the pressure, and if you go along the bottom here, you're increasing the temperature. So if you had water at a very high pressure and a very high temperature, you could see what the pressure was and see what the temperature was, and there would be a dot here, and you say, oh, the water is going to be a gas. Let's make this a lot simpler by just focusing on one particular pressure, this strip across the middle of the chart here. Now what I'm looking at here is normal atmospheric pressure, so that's the pressure of all the air in the room around you. Pressure is measured in something called millibars, and although it goes up and down, as we'll talk about in a minute, normal atmospheric pressure is at 1013 millibars. Now that was the pressure in the kitchen in the first edition we had, where I was melting the ice and then heating the ice up. So let's have a look and see what the phase diagram says should happen. And here at a low temperature is the ice, and as we let it warm up, it moved along here and it got to this point, which is 0 degrees centigrade, which is called the freezing point of water. And at that point, the ice started to turn into liquid water. And then you remember we turned the gas on and the water got hotter and hotter and hotter until it got to this point, which is 100 degrees centigrade. So this is called the boiling point of water. And at that point it was starting to bubble away, you remember, in the pan, and it turned into steam as water vapour. So it turned into a gas. So you see here the phase diagram is telling us at what temperature the water is going to go from a solid to a liquid and then to a gas. Now what would happen if we repeated that experiment but at a lower pressure? So this time the line we're interested in wouldn't be this one, it would be this one down here at a lower pressure. And can you see here that if we started along this line, here's freezing point, and we'd have to warm up the ice just a little bit more in order for it to turn into liquid water. But then when we turned the gas on, we heated it up, we'd go along here and look, you can see where we changed from a liquid to a gas. That's a lot less than the normal boiling point of water that happened in the first experiment. So you can see here that the water is going to boil at a much lower temperature because of the lower air pressure. And if you want to think about what's happening there, then you remember we talked about when we heated the water up, all those little water molecules were trying to get out of the water and escape because they had enough energy. Well, if the air above them is a lot thinner, it's a lot lower pressure, then there's not as much effort for those water particles to jump out of the water and turn into water vapour and disappear into the rest of the room. So that's why it is happening like that. So hi, we're all back together now, and what I'm going to do now is try a little experiment just to show that effect happening. That if you reduce the pressure, then water will boil at a lower temperature than normal. Okay, so what I've got for this experiment is I've got a syringe here, and what I'm going to do here is I'm going to put a bit of hot water. I've got hot water in here. It's not boiling, look, I can put my finger in it, and then I'm going to suck some of the water into the syringe like this. So there's water in there. Let's get a little bit of air out of there. There we go. And then what I'm going to do is I'm going to block this end so that no air can get in there and pull up the plunger like this. And what that's going to do is it's going to reduce the pressure in this part of the syringe. So the water is going to see a much lower air pressure. And what that should do is it should make this water in here, which is not boiling, look, you can see no bubbles or anything, it's going to make that water boil again. Right, so here we go, and I'm going to put it on this rubber glove here so we stop any air getting in, and then I'm going to pull up. It's going to take a lot of effort. I'm going to try pull up and see if the water boils. Get ready, let's turn it around so you can see the clear side. Here goes. Look, can you see? The water is boiling. Let's push that down again. Right, let's try again, here we go. Look at that. The water is boiling inside the syringe. And that's because, like on that phase diagram, we're at a lower pressure inside here. And so the water wants to boil at a lower temperature. And that's why if you're a mountain climber at the top of a very tall mountain, it's very difficult to make a good cup of tea. There. Because the air pressure at the top of a mountain, like Mount Everest, is a lot lower than it is down at sea level. So water boils at a much lower temperature, about 70 degrees centigrade. So you can never get the water hot enough to make a good cup of tea. Interesting, isn't it? Now, it's worth remembering that although normal atmospheric pressure is 1013 millibars, it does go up and down. And if you look at a weather map on the television, then the weather person will often talk about these H's and L's on the map as high and low pressure areas. And the air is always moving around in the atmosphere making weather. And the high pressure area is more air kind of bundled up and pushing more pressure down on the earth than areas of low pressure. If you want to think of the duvet, it's like somebody's getting an extra layer of duvet over here, and this person over here has got a lot less duvet pressing down on them. Maybe they've got cold feet in bed. What that means is if you look at the weather map and you find your house is underneath a low pressure area, then if somebody's got a cup of tea in your house, it's probably ever so slightly cooler than it would be for somebody who was underneath a high pressure area. It's time for the crazy Grandfad quiz to find out how much you've learned. Question 1. As well as how hot it is, what else affects the boiling point of water? And the answer is the pressure of the air around the water. Question 2. Does water boil at a higher or a lower temperature if the air pressure is low? It boils at a lower temperature. Question 3. Why can't you make a good cup of tea at the top of Mount Everest? Because the air pressure is lower there, and so you can never get the water hot enough. Question 4. Is the air pressure in your house always the same? No, it goes up and down depending on the weather. And question 5, this is for the science boffins only. What is this called, and what does it tell you? It's a phase diagram, in this case for water, and it tells you for the water at a certain temperature and pressure whether it will be a solid, a liquid, or a gas. So how did you do? Again, don't worry about it if you got some right or some wrong. It's not a competition. But hopefully you learnt something here about the science of water. Next time we'll move from the physics of water to the chemistry of water. And what makes it up and why people sometimes you'll hear refer to water as H2O. See you next time. Bye.